Hi guys, welcome. My name is Raghuram Reddy and I'm here with IBIS Prep. Today we will be learning about radioactivity and nuclear chemistry. So what is isotope notation, right? Isotope notation is in this form, ZAX. And the way I remember is there's this restaurant called Zaxby's, really good chicken. But what's important is right here, Zax. So you kind of go in this clockwise direction. So Z is the atomic number and that is the number of protons. And then A is the mass number or atomic mass, and that's the number of protons plus the number of neutrons. And then X is just the element symbol. So for 12 carbon, you have it written as 12, 6 carbon. So isotope notation is really important because you're going to be using it in these radioactivity equations. And the first radioactivity equation that we will be talking about is the alpha decay. And what happens in the alpha decay is a parent nucleus goes to the daughter nucleus and alpha particle. And this alpha particle is denoted by the helium nucleus, the 4,2 helium, or it can also be written as 4,2 alpha. And the daughter nucleus, what happens to the atomic number is that it decreases by 2, and the mass number, it decreases by 4. So the electron is denoted by 0, negative, 1e, or as B negative, as you can see up in top. And nu is the symbol for a neutrino, and that's right here. This is nu. And this line above it right here, that is anti. And so this is an anti-neutrino. And the neutrino was named, got its name because it's electrically neutral. And the mass is so small, which is where the eno part comes from. And the last thing is that it has a spin of positive 1/2. So now that we have talked about beta negative decay, let's talk about beta positive decay. And beta positive decay is often called positron emission. And that's because it emits this positron molecule, which is 0 plus 1 E. And it also emits a neutrino right here. And for all these radioactivity equations, it's very mathematical in the sense that this arrow kind of represents an equal. So you have 37 equals 37, and then you have 19 equals 18 plus 1. So you want to kind of balance both sides. So let's move on to electron capture. And I really want you to pay attention to the word capture, right? Because this is different from decay. So for decay, you have the alpha particle, the positron or the electron on the right-hand side of the equation. But for capture, electron capture, you're going to have that electron on the left side because you're capturing the electron versus emitting it. And when you capture this electron, you're going to produce a daughter nucleus, but you're also going to emit a neutrino. And last but not least, this is my favorite. It's called gamma decay. And why is it my favorite? It's because it's so easy to solve any equations that are gamma decay. And so what happens in a gamma decay? You start off with this excited nuclear state. And so that nucleus changes from an excited state, a higher energy state right here, to this lower energy state through the emission of electromagnetic radiation. And so this excited state is often denoted by this AM. You're going to see this M, or you could see this star. In some cases, they might not include the star or the M. They'll just have both of these the same. But this is the correct way to write a gamma decay equation. Either have the M or the star. And you're going to release a gamma ray, which is a 0, 0 photon, a gamma. So to recap, we have alpha decay, beta positive decay, beta negative decay, positron emission, and electron capture. And if you found this video to be helpful, please subscribe, like the video, and leave a comment. And also feel free to visit our amazing website, ibisprep.com, for any tutoring services that you may need.